Hey AP Calc students! Today's video is reviewing trigonometry. And what other place to start when reviewing trigonometry than with your beautiful unit circle? Oh yeah! So I see a blank unit circle. There are degree angles in there though. I was kind of nice and I gave you the angles in degrees. I want you to complete the unit circle with the angles in radians. So find all the radian angles, and then also find the coordinates. So this one might take you a little longer. I really want you to reach back into the depths of your memory and remember your unit circle. Welcome back. So I'm gonna remind you of a little trick for finding the angles in radians. So we know that in a full circle, the circle starts at 0, and then the full degrees is 360 or 2 pi, right? That full circle is 2 pi. And so half of a circle is 1 pi. So right there we have pi. And you can keep kind of dividing the circle up like this in order to get the other radians. So this one would be pi over 2. And then pi over 2 divided by half at 45 is pi over 4. To get these other angles, I see to go from 90 to 30, you divide by 3. So you can divide pi over 2 by 3. So pi over 2 divided by 3 is the same as pi over 2 times 1/3. That's pi over 6. And then two 30-degree angles makes 60, so 2 pi over 6 is the same as pi over 3. So if you know your fractions really well, you can easily get this. I hope that you didn't just convert all the degrees to radians. This would take forever if you had to convert from degrees to radians for all of these. Memorize them. So I'm just going to show you the first quadrant. To get these coordinates, where they come from is that there's a triangle here, right? And so I can call the base of the triangle x and the height of the triangle y. And so in order to get the sides, we could use trig ratios. So for instance, I know that if this is a unit circle, we're just going to call the hypotenuse 1, right? So I could set up a trig ratio. Sine of 30, sine is opposite over hypotenuse. So sine of 30 degrees, or sine of pi over 6, is our y value. And if I were to plug that into the calculator, I would get this y value is 1/2. So that is the y coordinate, 1/2. And then I could do cosine of the same angle, pi over 6, but now it's equal to x, because cosine is adjacent. The adjacent side is x over the hypotenuse y. And I'm going to plug this into a calculator, and I would get square root of 3 over 2. Whew, running out of space. So this coordinate is square root of 3 over 2. Okay, so this is something you should memorize. The short side of a 30 or 60 degree triangle will be 1/2, and the long side of a 60 or 30 degree triangle will be square root of 3 over 2. So I can very quickly get this coordinate up here. It's just going to be switched. The x is now the short side, and the y is the long side. And then for any 45 degree angle, or pi over 4, anything that's pi over 4, will be square root of 2 over 2 and square root of 2 over 2. The coordinate right here, the x coordinate goes all the way out to 1, and the y coordinate is 0. And then the coordinate right here, the x coordinate is 0 because x didn't move, and the y came all the way up here to 1. Okay, so there's my first quadrant, and hopefully that's kind of bringing back some memories for you. And so if you weren't able to fill this out before, like if you had a lot of blank spaces, I want you to try to finish filling out this whole thing using the symmetry of the unit circle. So use the symmetry of the unit circle to use what we have in quadrant 1 to finish this off. So keep working on this warm-up. At this point, I'll put you out of your misery if you haven't gotten the unit circle yet. Here it is in all of its glory. So you can see the degrees and the radian angles. So the radian angles always have a denominator of 6, 4, or 3. So like across, directly across from a pi over 3 is another pi over 3. Or directly across from a pi over 6 is another pi over 6. So kind of use that symmetry that you know. And then of course the coordinates, once you memorize these 3 coordinates right here, they are the same all the way around. You just have to change the negative signs. So obviously in quadrant 1, the x and y coordinates are both positive. In quadrant 2, x is negative, y is positive. In quadrant 3, both x and y are negative. And in quadrant 4, x is positive, y is negative. So there's also the little reminder of the signs. The coordinates stay the same, the signs change. Okay? I also provided on this page a quick definition of what a unit circle is. A unit circle is a circle that has a radius of 1 unit. So all the radii in the circle is just 1 unit, and it's centered at the origin. So in the xy plane, it's centered at 0, 0. Okay? If you don't have these memorized, memorize them. At least memorize quadrant 1, and then you can use the symmetry around the circle to figure out the rest of the circle. Okay, so we're going to be applying the unit circle in the next page. Okay, so using trigonometric ratios in the unit circle. I touched base on this a little bit in the warm-up, but here is all the info you need if that was a little bit confusing. Okay, so basically you'll use the xy coordinate to find the lengths of the opposite and adjacent sides of a triangle formed in the unit circle. And so our trig ratios, which hopefully you all have SOHCAHTOA memorized by now, so SOHCAHTOA, right? SOHCAHTOA are our trig ratios, right? And so we can fill in the table with the appropriate side. So sine, as I can see in SOHCAHTOA, is my opposite side over my hypotenuse. Cosine, ka, is the adjacent side over my hypotenuse. I totally did not spell hypotenuse. My brain is distracted. Let's spell hypotenuse correctly this time. Hypotenuse. Hypotenuse. There we go. This one, I wasn't given the trig name. I need to fill that in. So opposite over adjacent is my tangent. Okay. Cosecant. Cosecant is the reciprocal of sine. So cosecant is 1 over sine, which means I can just flip my trig ratio for sine. So it's hypotenuse over opposite. This one, which one am I missing? Cosecant, I have cotangent, so I'm missing secant. Secant is the reciprocal of cosine. So the reciprocal of cosine will be hypotenuse over adjacent. And then cotangent is the reciprocal of tangent. So the reciprocal of tangent is adjacent over opposite. Okay. And so it's easy to see in this first little picture, in this first graph, what like the opposite, the adjacent, and the hypotenuse are. So the hypotenuse in the unit circle is always 1. That's easy. And then this x side is the adjacent. So x is always your adjacent side, and y is always your opposite side. Okay? And so this kind of translates into our coordinates. So this just is a random angle, 37 degrees. So apparently a 37-degree angle has an adjacent side of 4/5 and an opposite side of 3/5. And so those side lengths become the xy coordinates. Okay? And the xy coordinates and the side lengths, same thing. We are going to use those with our for our trig ratios in the unit circle. So instead of always saying opposite or hypotenuse, now I can say that y is y over 1, which is just y. Since the opposite side is always the y coordinate, my sine value is just whatever that y coordinate is. And my cosine value is x over 1, adjacent over hypotenuse. The adjacent side is just x, whatever your x coordinate is in the unit circle. Okay? Then tangent is y over x, opposite over adjacent. Cosecant is the reciprocal, so the hypotenuse over opposite. The opposite side is always y. I have 1 over x for secant. And then cotangent will be x over y. And so these are the ratios that I am going to use to replace the values of sine. Okay? So in this case, if you need like a little mini example, I'll do it in red. If I were to say like, what is sine of 37 degrees? Sine of 37 degrees is the y coordinate, 3/5. The y coordinate. And then if I were to say, what is tangent of 37? That's going to be y over x. So y over x is 3/5 divided by 4/5, which is 3 over 4. Okay. So this is how you use the coordinates to solve trigonometric ratios. Okay. Usually we don't have random angles like this. We have angles in the unit circle, like all of our special angles that are in the unit circle. So those are the ones that you need to memorize. Okay, so here are some examples of how to use trig ratios to solve trig equations. So the first one, A, is a simple trig equation where I have to figure out what is the value of cosine of pi over 6. I usually always do a quick sketch in my head, not always on paper. If you want to do a sketch on paper while you're still memorizing, that's great. I think the goal is try to have this image in your head. And so cosine of pi over 6 is this low angle right here. And then I know that the coordinates will be square root of 3 over 2 and 1/2. And so cosine, I need to remember cosine is my x coordinate. That's the x coordinate. So since cosine is the x coordinate, I'm going to use that value right there. So I can say cosine pi over 6 is equal to square root of 3 over 2. I hope that's coming back to you a little bit. And so part B, this might look like a little bit of a mess, but really what we have to do is we have to try to get this trig function by itself. So just like in A, how I just had cosine of pi over 6 equals x, I want to get the trig value by itself. So I'm going to do some math, some algebra, to get that by itself. Oops. So I started off by adding square root of 2 to both sides, and then I'll divide by 2 to get sine of theta equals square root of 2 over 2. So then I need to figure out when is sine at what angle. So at what angle is the y coordinate, because sine is the y coordinate. Square root of 2 over 2. When is the y coordinate square root of 2 over 2? That's going to be right here and right here. So I have square root of 2 over 2 comma square root of 2 over 2. And here I have negative square root of 2 over 2, square root of 2 over 2. So in both of these, I'm looking for the y coordinate. There's my y coordinate in its proper value. So I have two answers in this case. I have theta equals pi over 4, and I have theta equals 3 pi over 4. Okay, because those are the two angles where the y coordinate is equal to square root of 2 over 2. So now I hope you're remembering, like, oh yeah, it's really important I have this unit circle thing memorized, otherwise I won't be able to recall all these angles and coordinates so quickly. Yes, it is very important. Okay. C is a little tricky, I'll be honest. So again, I want to get the trig ratio, or the trig function by itself. And so my first step is going to take the square root. So when I take the square root, I get tangent of theta, and then the square root of 1 is both plus and minus 1. And so I need to know when is tangent of theta equal to plus or minus 1. And I want to remind you that tangent is the ratio of the y coordinate over x. So it's the y over the x coordinates. So it's a ratio. So I need to figure out where are the coordinates for tangent the same. And maybe part B will help you. So where are the coordinates for x and y the same so that tangent would equal 1? So looking here, find all the places where they're the same. And hopefully you can see that there, 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 and there. If I were to take the ratio of those coordinates, of the x and y coordinates, I would get 1 or negative 1 if I divide those, and it's because they're the same number. And so this is going to be true for theta equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay. And then one last trig equation. This one I don't have to solve. Just have to figure out what is secant of pi over 2. So I'm going to do another sketch. Oopsies. Pi over 2 is right here. It's that point right there. And I know that the coordinate here is 0, 1. And so secant. What is the trig ratio for secant? It's the reciprocal of cosine. Cosine is x. So secant is 1 over x coordinate. Secant is 1 over the x coordinate. Okay, so my x coordinate in this case is 0, and so secant of pi over 2 will be 1 over 0. We can't divide by 0, so this is undefined. That answer is undefined. Okay. I know this was a lot of problems all at once. Hopefully this is touching base on some of the problems that you remember from last year in pre-calculus.